let's talk a little bit more about properties that you could hope to extract from either a molecular dynamics or a Monte Carlo simulation. So some properties you just get straight up from an average over all the either time steps in molecular dynamics or Monte Carlo steps. So for example, the energy is typically something that I can compute directly from the simulation. Internal energy U is just an average. I might also use the symbol E. It's just 1 over m if m's the number of time steps and the energy at each time step. So there's really nothing to do here. It's very, very, very simple. Heat capacity is a little bit more complicated. You can monitor the heat capacity, though, to look for evidence of phase changes, like from a solid to a liquid. We mentioned melting earlier. Any first-order transition is going to lead to an infinite heat capacity, whereas a second-order transition leads to a discontinuous jump in the heat capacity. So monitoring the heat capacity is kind of a useful thing in these simulations. How can I get it? Well, I can monitor the internal energy U at different temperatures, and I may need to run different simulations set at different temperatures if I'm running simulations that keep temperature constant. But from those simulations, I can numerically calculate the derivative of U with respect to T at constant volume, and then that will give me the heat capacity at constant volume. Or I could use a formula like this. I could look at the average, that's the outer brackets, of the square of the energy minus the average energy. So this is like variations of the energy during the simulation, and divide that by kBT. That can also give me the heat capacity at constant volume. So there's a couple different strategies. Pressure I can get out of a simulation as long as I haven't somehow engineered the simulation to have a constant pressure. But in an ideal gas, you might remember PV equals nRT. This is a slightly different way to write that, where I'm using N as the number of particles and Kb the Boltzmann constant. And there I'm just using the fact that the Boltzmann constant times Avogadro's number is R, and so this is the same as this. But either way, if I had an ideal gas, we have these well-known formulas. And what does an ideal gas assume? Well, if you think back to freshman chem, and if your freshman chem professor talked about what goes into assuming an ideal gas, or maybe you learned this in physical chemistry, an ideal gas basically assumes there's no interactions between molecules, which is of course wrong, right? Molecules actually have at least weak London dispersion interactions between them, if nothing else. And so the force between molecules I and J is not really zero, and that's going to lead to a deviation from the ideal gas behavior. So then I could rewrite this and saying, instead of saying P equals 1 over V times N kBT, which is this first piece, I say it's that minus a correction factor. And in fact, if the molecules are attracted to each other, then that tends to decrease the pressure that they exert by colliding with the walls of the container. So it's a negative correction. And I sum over all unique pairs of atoms, I and J. So say I greater than J just to get the unique pairs and not double count them. And there's a 1/3, because I guess there's 3 degrees of freedom. And that will give me a value for the pressure. Now these forces are already a byproduct of a molecular dynamics simulation, because you remember you need the forces on all the atoms. So if you did an MD simulation, you already have these Fs and you can throw them into this formula and compute P. If you're doing Monte Carlo, you don't have these forces, and so you'd have to do some extra work if you wanted to get that. Temperature, I could also compute if it's not fixed in the simulation. So if I'm doing a canonical ensemble and VT is fixed, then T is fixed and I know what it is because the user tells the simulation what it is, not the other way around. However, if I were doing a microcanonical ensemble where I fix N, V, and E, then the temperature is free to fluctuate. And so I might want to calculate it and see, well, how hot is the simulation and how steady is it? So I could get the temperature by how it's connected to the kinetic energy K. And one way to write the kinetic energy is, of course, 1/2 mv squared. Another way, knowing that P equals mv, is to say it's P squared over 2m, and I'll say sub I, where I is each particle. So that would be a way to do it, and it turns out this can be written this way: kBt over 2 times quantity 3n minus nc, where nc is the number of constraints applied to the simulation. And in an MD simulation, you normally keep the total linear momentum of the entire system set to 0, meaning your simulation box isn't going anywhere, okay? And that will typically lead to 3 constraints, and so NC would be then 3. Okay, so that gives you a formula to compute temperature. Now, what else can you get out of these MD or MC simulations? One very useful property is called a radial distribution function. And this is a really great way to try to analyze condensed phases like solids or liquids, to compute this radial distribution function, which is often called G of R. Okay? And the idea basically is to say, if I have some particular atom or molecule that is at the origin, so this red molecule, say, then what I want to know is how likely is it that there are other molecules at certain distances away from me. Okay? And so I look at some distance r, and I say, well, what's the probability that I've got other atoms or other molecules at that particular location away from me? And so these are radial distribution functions, so I average over all the angular coordinates, and I'm just looking at different shells, radial shells, as I go out. Now, if I had a perfectly homogeneous system that was, spread out smoothly in space in all directions, and if it's isotropic, meaning it's the same in x, y, and z directions, then I would expect that it's got to be roughly just the average density of the particles, because if it's all totally smooth, then I know what's the probability of finding a particular particle at any given point in space. It's the same if it's isotropic and homogeneous. And so there, the density is just the number of particles divided by the volume. And that gives me kind of a baseline of what I would expect. Now, in reality, matter is not just a smooth jelly. It's made of atoms, right? And so I have to have wiggles in G of R depending on if I hit another atom or if there's an empty space where there's not an atom. So relative to some reference particle like this red particle, the probability of finding another particle at distance r is rho times G of R. So G of R basically tells me how to tune or adjust the baseline density or the baseline probability for the fact that matter is actually made up of actual atoms that I either hit or I don't. Okay, so basically G of R is a multiplicative factor showing you a local increase or decrease relative to the baseline probability given by the density. And if I go to very long range, then basically the probability of running into another particle should be governed basically by the average density. And so G of R should approach 1 at large r, because I've got a very big sort of radial shell, and the microscopic details of the atom level picture then kind of wash out at very large r. And so here's an example graph from Wikipedia where you can see here's G of R for some model fluid, and at long range you see that we're hovering around 1, which is like what we were talking about here. At short range, then I see these big deviations. So how do I understand this? So below 1, this is in some normalized units, r over sigma. Below 1 in these arbitrary unit scale, there's 0 probability of running into another particle. Why is that? Well, if I'm too close to the target particle, to the origin particle, then I can't run into another atom yet because they're not infinitely squeezed next to each other. So there's no chance that I run into another particle. And you would expect that to be true at least for up to a radius equal to the radius of the particle itself, because nobody's going to be collided inside the red particle. So there's got to eventually be 0 probability of finding another particle. Then suddenly, once I break outside the radius of my target particle, then other guys might be nearby. And so then I see a rapid increase. In fact, if I go a little farther out, then there's a high probability that other things are nearby. So it goes way above 1. And then it drops back down if I go past this sort of first solvation shell, if you will. Then there's going to be a hole before the second solvation shell can slip in. And of course, these are all mixed together in a liquid, and it's a little more complicated, but you can kind of understand the basic idea of why it might dip after the first increase. And then these peaks basically correspond to different solvation shells, if you will, around the particle, and they damp out and get smaller and smaller as you get further and further away. Okay. And knowing G of R is very useful in terms of analysis and understanding and predicting things. It's really a classic quantity people want to get out of their simulations. Now, I kind of pretended on the last slide everything was an atom. Of course, everything's not always atoms. I might have water, where each water molecule is made out of oxygen and 2 hydrogens, and there, how do I deal with this radial distribution function? Well, I could just do 3 radial distribution functions. I could have one that tells me for a given oxygen how close are all the other oxygens, so that would be an OO1. I could say for a given oxygen how close are all the hydrogens, that would give me an OH. Or I could say from a given hydrogen how close are the other hydrogens. And that would give you the 3 possibilities in liquid water, for example. Or you could try to have a version of this talking about how far from a given molecule, how far apart is another molecule, but then I would need, to deal somehow with the orientation of these relative to each other to have full information. Okay, so I could do that. Now, if I assume that all the forces are pairwise additive, which you do in a lot of force fields, which is not quite true due to polarization, but to a good approximation, forces tend to be pairwise additive, and a 3-body effect in a lot of systems isn't necessarily too large. Under that assumption, I can use G of R for some interesting things. I can give an ideal gas part of some properties, and then a correction computed via G of R. And so, for example, the energy of a system is something like 3/2 in kBT plus some correction, 2 pi n times rho, the density, times this integral, where I'm looking at the potential V of R between some particles, and G of R, this radial distribution function. Or likewise, PV has the sort of a similar integral that involves, in this case, the derivative of V of R times G of R. So it's useful for computing some properties if you have it, as well as just understanding the structure of the liquid or the solid. Not all properties are as easy to compute as others, okay? So things like E and P and C sub V are sometimes called mechanical properties because they're sort of relatively easy to compute from MD or MC. because they're directly related to the partition function Q. And the partition function reigns supreme. If you have that, you have a lot of things. But there are other properties like entropy or free energy or chemical potential that don't depend directly on Q, but rather on derivatives of Q. And it turns out these derivatives tend to have larger contributions from the high energy configurations than just straight Q does. And so there, it's a little trickier, because if you bias your techniques to try to sample more effectively the low energy, more probable configurations, then they might be missing a little bit of the high energy, lower probability things that can make a little bit bigger contribution to the derivative of Q compared to just Q. All right, let me say a little bit about the computational cost of running these different MD simulations or MC simulations. If we're using force fields, which we typically are, or molecular mechanics methods, then it's these non-bonded terms that tend to be the expensive ones. And that's exactly what we mentioned when we talked about force field methods. Because you need these naively for every pair of atoms. If I've got a London dispersion interaction that goes into a van der Waals term, then, on paper, I need this for every pair of atoms. If they're n atoms, then I need n squared of those, and that could be a lot if n's a large number. Now, for the Lennard-Jones potential in particular, if you call sigma the distance at which the potential crosses zero on the repulsive wall, then at a distance of 2.5 sigma for the Lennard-Jones potential, the potential energy is less than 1% of the well depth epsilon. So you could kind of cut things off essentially at that distance or a little bit bigger distance, and you're not making much of an error. So you can not literally compute the Lennard-Jones for every pair of atoms, but you could go out to some distance and say beyond that, don't really need it because I'm making minimal errors. You can do a similar thing with electrostatics, but the problem is Lennard-Jones dies off as 1 over r to the 6th, electrostatics dies off as 1 over r, so it's a slower decay, and your cutoff distance would have to be much bigger, maybe like 10 angstroms or maybe more. There are other mathematical techniques to deal with that, lattice sum techniques or Ewald summation techniques that are a little beyond what I'm going to discuss, but that's what you would want to do to account for those long-range interactions. And these kind of interactions are going to dominate your computational cost just because there's more of them. Another thing you can do to reduce the computational cost is to use what's called the minimum in an image convention. And that basically says each atom interacts only with a single image of an atom. So that's a situation where you basically have some kind of cutoff radius, say, and you say that the reference atom here in red, maybe interacts with this blue one and this blue one and this blue one, but not all the replicas of those atoms. So, for example, this blue one here is the same as this blue one here. And in the minimum image convention, you say that, well, this guy already sees this one, which and this one is just an image of that one, so I only include those guys once and not all their replicated pairs everywhere. Now, for this to make any sense, the box length would need to be at least twice as big as the largest cutoff distance. But you could enforce that by using a slightly bigger box length. Okay, so that's one way to sort of simplify things. And then let me just say a little bit more technical things about how you would construct an algorithm to try to account for some of these things and to make the computation more practical. One of those is to talk about the non-bonded neighbor list. Okay, what does that mean? Well, if I'm trying to use something like a minimum image convention or whatnot, and have cutoff radii, then I need to know how far apart all the atoms are, right? Because if I've got some cutoff and I say everything within that cutoff I'm going to include, everything outside that cutoff I'm not going to include, I need to know how far apart all the atoms are. But that's a problem, because to know for every atom how far apart every other atom is an n squared computation, and that's what I'm trying to avoid. I just mentioned on the previous slides that n squared is a large number, and I want to avoid that. So what do? Well, I can use a trick called a neighbor list, and that's going to help me know, do I need to compute this distance to the next atom or not? And if I don't need to, then I'm not going to do it. So how would this work? Well, first off, I do begin computing the distances between all pairs of atoms. So that's expensive, but I'm going to try to minimize the number of times I do this. So I will do it up front. So I've got an upfront n squared calculation, which is tricky, but then hopefully now I can be smarter in the next steps. So from that list of distances, I make a list of all the atoms that are nearby each atom. So for every atom, I say, who are my neighbors? Who's within a certain cutoff distance, okay? And I use a cutoff distance that's larger than the one I need to cut off, say, my van der Waals terms. So that gives me what's called a buffer region, where if I want van der Waals interactions within 6 angstroms, maybe my neighbor list goes out to, who knows, maybe 8 angstroms. I'm making up some numbers, but I go out a little further than I really need to have a buffer region. Then, on the next few molecular dynamics steps, I only update the distance information for the neighbors of each atom. So if I know this guy has 4 neighbors that are within this neighbor cutoff distance, then I only update those distances and not all the distances, which would be very, very costly. And if I'm only updating a handful of them for each atom, then the cost of that is way less. That is going to allow me to watch if any atoms move from the buffer region into my van der Waals cutoff region, and if they do, then I need to start including that in my van der Waals calculation. Or if they move out of the van der Waals region into the buffer region, or maybe out of the buffer region, out completely. I can do that if I monitor all the ones in my neighbor list cutoff. Now, what's the danger of this? Well, the danger is I might have things that are not on my neighbor list that have suddenly moved into the buffer region, and I won't know that because I'm not computing all distances. So every so many steps, maybe 10, maybe 20, I need to reconstruct the neighbor list from scratch to account for the fact that maybe some guys now have moved close enough to be on my neighbor list. And this is obviously not perfect, but saves a giant amount of computer time. You can use a few tricks, and I'll just give you a sense of what they might be. You could, for example, instead of recomputing the neighbor list every 10 or every 20 iterations, you could try to use information from the simulation itself to guess when you should update them. You can watch, well, on average, how often are the atoms moving? And that should tell you something about how often you need to be updating your neighbor list. Each time the neighbor list is updated, you can zero out an array that stores the atomic movements, and then each time step you can update that array with how much each atom has moved, and then the sum of the movements of 2 atoms, if that exceeds the buffer region length, then that tells you it's probably time to update the neighbor list. So I hope that makes sense. There's also something called a cell method, where for very large systems, even updating the neighbor list every 10 iterations is just going to be too costly. And so there, what you want to do is divide your simulation system up into boxes or cells, and then for an appropriate choice of a cell size, the neighbor list only needs to include atoms, pairs of atoms that are either within the same cell or within adjacent cells. So if I know this guy is, 3 cells away, and if those cells are fairly large, then I know I don't need to compute this distance even every 10 or 20 iterations, because it's just too darn far away. And this would be the more modern and better way to do it for large scale simulations. Of course, I do have to keep track of which cell is each atom in, but I can do that. Okay, well, that gives you a little hint a bit about some of the algorithmic tricks that people use to make these calculations more practical. But I hope this introduction gives you a little bit of an idea of the kinds of things you can get out of molecular dynamics and Monte Carlo, and a little bit about basically how they work. The simple ideas of molecular dynamics and Monte Carlo are really not very complicated, but there are a lot of tricks and techniques to make them actually work in practice.